composite functions. Whenever we talk about composite functions, we talk about its domains too as well. And a domain just simply means that what's going to cause a restriction on that function from being a real number. So I'm going to look at my first function here, which is called f. And I ask myself, whatever I plug in for x, will it yield a real number, or will it yield some number that's imaginary, doesn't exist, it's not real, undefined? So in this particular case, whatever I plug in for x times 6 minus 3 is going to yield out a real number no matter what. So my domain here is going to be all real numbers. So negative infinity to positive infinity. So let's look at the function called g of x. So this function of g says that I have x plus 3 divided by x. Or 6, sorry, not x, 6. But whenever I look at it, I see that this is a ratio, it's a fraction. And this means that it may have some restrictions because there's things you cannot have in the denominator. 1 is 0. 0 causes it to be undefined. The other issues can be worked out, like square roots, negatives, fractions, decimals. And imaginary numbers, we can work with those. But if it yields a 0 in the denominator, then therefore we cannot come up with a real number. It's going to be undefined. So I look here and I see, is there a variable in the denominator? And in this case, I'm going to say no, it's just a constant number of 6. So therefore, this domain is going to yield a real number every time I plug in something for x. So I'm going to call it negative infinity to positive infinity. However, if it did have x in this denominator, then we would have to solve for x to see what it cannot equal. So I just want to do a quick example. So say it was, and this is just an example, a little note to the side. Say that x minus 1 is in the denominator. And let's just put this on top here. Say it was. I would have to take what's in the denominator, set it not equal to 0, because that means we can't have it equal to 0, right? And solve. Well, I'd have to add the 1 to both sides to get x by itself, and it would say x cannot equal 1. So I would set this domain up as negative infinity to 1, parenthesis, and it's going to union 1 to positive infinity, meaning that I can have all numbers smaller than 1 and all numbers bigger than 1 and still come out with a real number. However, I couldn't use 1 because 1 would give me 0 and that's undefined. So this is what I meant by looking at that fraction. And in this case here, this fraction just has this constant number in it. It's not no variables. So moving on. So let's talk about g of f and f of g. Clearly, f of g of x just clearly says that whatever my function f is, everywhere as I see x, I'm going to plug in the g of x function. So I have f of x is equal to 6x minus 3, correct? Well, I'm wanting to plug in my g of x everywhere as I see that. What is g of x? It is x plus 3 divided by 6, all equals 6x minus 3. Well, what happened? I got to plug that in for my x. So let's give some space here. And let's change this up a little bit. I got x plus 3 divided by 6. And then we're going to use the rules. If we can combine anything, clean it up in the parentheses. In this case, there is no like terms. But what I see here is this 6 out front can be over 1. 6 divides 6, right? Because I'm going to distribute that into the inside. That reduces down, and this turned out really nice and pretty. So now I have 1 times that parentheses. So and that parentheses is divided by 1, so it's just 1 times x times positive 3. And this is what I get. This worked out really nice. And now let's combine any like terms, and I notice that positive 3 and negative 3 goes to 0. And my answer here is just x. And my domain here is all real numbers. And we're going to do the same thing for g of x. So I'm going to take my g function. Everywhere as I see x, I'm going to plug in my f of x function, and then we're going to clean it up.